Hi, and welcome. I will talk today about synthesizing specifications for robotic tasks from one example and the natural language description. Let me introduce the co-authors of the paper, Eva and Rupak, my colleagues from MPI for Software Systems. My name is Ivan. It is unfortunate that we cannot meet in person, but all three of us will be around online. There is a promise made to humanity. A promise of robots delivering medications in hospitals, bringing food and drinks, delivering post, or cleaning streets. All the while, humans will sing and dance, play sports, think about the meaning of life, and make love. Many scientists have worked on that promise in various directions. One direction is synthesizing a correct robot's behavior from formal specifications. The three works mentioned here are an example of that approach. Their formalism for specifications is LTL, linear temporal logic. Given an LTL specification, they synthesize the robot's behavior that adheres to it. The only problem is, where does this specification come from? LTL is infamous for how easy it is to get it wrong, especially for non-experts. In this paper, we solve the problem by helping users derive the specification that matches their intent. We help them do so by a synthesis toolchain LTL Talk. LTL Talk uses LTL as its underlying formal language, but accepts user specifications in the natural language, and through the process of interactive synthesis, it determines the correct specification. It learns from this interaction in the process of grammar expansion. The user's natural language expression becomes a first-class expression in the underlying formal language. We implemented it in the simulation world containing items of different colors and shapes that the robot can collect. There are three main advantages of LTL Talk's approach to instructing robots. It does not need a large training set. It only asks its user to provide a single example for a given command, and it adapts to the language of its users, while at all times preserving an interpretable grammar. I will demonstrate now how LTL Talk can be used. As I mentioned, the items in the simulation environment are of different shapes and colors. Each tile of the environment is either wet or dry. The robot is represented by the gray cube. LTL Talk accepts LTL specifications such as eventually pick one X circle item at 7.4, which means that the robot should pick a circle of any color. After planning for a bit, the robot executes the specification. However, what if the user is not familiar with the formal language? What if the user writes something more natural, for instance, get one circle item from 7.4? Now, the system will ask the user to demonstrate the desired behavior. The user does so. The system will now offer several animations for the user to judge. Do they match the original intent? Picking a yellow triangle does not match it, discarding it. This animation does match, accepting it. After receiving this demonstration, the system is now able to understand the original expression, but also grammatically similar expressions, such as get two triangle item from 10.8. Below, the system provides its LTL interpretation of the command. Coming back to the high-level scheme of the system, let's first dive into the interactive synthesis module to see how LTL Talk determines what is the correct specification corresponding to the user's natural language command. The synthesis starts from a natural language description and the user's demonstration. Because synthesis from a single example is an underspecified problem, we use a heuristic method to generate a sample containing more examples. From that sample, we generate a set of specification candidates C. In order to narrow it down to a single candidate, we generate worlds and robots executions in them so that, based on the user's judgment on whether or not it matches their intent, at least one candidate can be eliminated. Eventually, there will be only one candidate remaining in the set, and that candidate will be returned. Let's now consider the individual parts of the system on our example. The natural language description in the example was get one circle item from 7.4. The user gave a demonstration as a sequence of actions. This demonstration is then turned into a trace containing all propositions that were true in each time step. We see that picking a green circle makes several propositions true. For instance, a circle is picked, an item of any color or shape is picked, and so on. Let's see now how we can generate a sample consisting of both positive and negative sequences from a single user's demonstration. We do so using two heuristic principles. The first one is the principle of no excessive trace. We assume that any prefix of the user-provided demonstration does not demonstrate the user's intent. The demonstration we had was a sequence of moves to the right followed by picking a green circle. From there, we infer that a sequence of moves to the right alone is a negative sequence. The second principle is the principle of no excessive action. This principle takes a complex action and assumes that any simpler action does not suffice. Consider a slightly modified example, where in the last time step two items are picked up. We infer that the same sequence, but with only one of the two items is picked up, is a negative sequence. Know that assuming these two principles is not assuming that the user is able to provide an optimal demonstration in any way. It is a weaker assumption, that the user will stop as soon as a correct demonstration is provided. So far, what do we have? We have generated a sample consisting of the positive sequence, the user-provided demonstration, and a set of negative sequences. The next step is to generate a set of candidate specifications using the sample and the natural language description. Let's dive deeper into how this is done. With the sample and the natural language description as inputs, we want to generate an SMT problem. A solution to this problem will give us a candidate LTL specification. We define the SMT problem as a combination of hard and soft constraints. The hard constraints enforce the consistency of the specification with the sample, while the soft constraints introduce a bias towards the natural language description. I will now describe both hard and soft constraints. This is the most technical part of the presentation, but I will be using examples to explain the constraints, so bear with me. I digress first and introduce LTL with a couple of examples. LTL is a logic for describing temporal relations in infinite sequences of events. For example, in LTL we can express that eventually proposition P will hold true. This is denoted by FP, where F stands for finally, synonymous with eventually. Let's evaluate the formula FP on this sequence. Under every tick, there is a set of true propositions in that time point. We see that there is a time point at which the proposition P is true. Thus, the formula eventually P is true for this sequence. Similarly, consider a formula P until Q. This formula describes sequences where the proposition Q eventually holds, and until that happens, the proposition P must hold. This exactly is the case on this sequence. Q holds at this time point, and P holds at every time point before that. In this paper, we are focusing on the co-safe LTL formulas. Those are the formulas that can be shown true by only observing a finite prefix of the sequence. Both eventually P and P until Q are co-safe. In the context of our robotic world, this formula is saying that the robot should eventually pick one item of red color and any shape from the field 7,4. Now that we have an idea of LTL syntax and semantics, let's define the hard constraints to ensure the consistency of the specification with the sample. We can visualize an LTL formula as a syntax tree. For example, this tree describes the formula P until Q and finally R. The first set of constraints are the constraints on the structure of the tree. We define one propositional variable per node of the tree and require that the arity of the operators is respected, that tree is connected, and that the maximum possible depth of the tree is delta, which is a hyperparameter of the algorithm. This captures structural properties. Now we need to capture the semantic properties of the LTL operators. We will create propositional variables that capture the truth value of all nodes for all possible time steps. For example, if we are interested in the truth value of the node marked with the operator f, finally, we have to observe a sequence of the syntax trees, one per time step. As soon as the f's child in one of them is true, indicated by green color, we can conclude that the inspected node is true as well. In the end, we need to connect our formula to the sample. For the positive trace, we assign the values of the propositions to the propositional variables corresponding to leaf nodes. Additionally, we require that the root node evaluates to true, as indicated by its green color. For each of the negative traces, we do the same, except that we require that the root node evaluates to false, as indicated by its red color. With these constraints, we capture the consistency of the specifications with the sample. Additionally, we would like to use soft constraints to favor a certain kind of specifications. First, we prefer simpler over more complex specifications. Thus, we require that an integer variable capital delta, representing the size of the specification, be minimized. Second, we want to bias specifications towards the natural language description D. In order to do so, we use a function age that approximates the similarity between the operator O and the description D. It does so by counting overlaps between the two, taking into account synonyms. Now, for every operator O, including propositional variables as nullary operators, we add the soft constraint that is telling us that the operator O should appear somewhere in the formula. This is why there is a disjunction over all positions in the formula, and with a weight corresponding to the function age. These constraints define our SMT problem. Every time we ask a solver for a model of the problem, we get one candidate LTL specification. In our running example, we get 4 candidates. How many candidates we get is again determined by a hyperparameter of the algorithm. The first 3 candidates correspond to eventually picking up an item described by different attributes, and the 4th one requires that the robot first steps into the water and then picks up a circle. Having obtained the set of candidate specifications, the system is narrowing it down to a single one by interacting with the user. We saw that the system generates worlds and the robot's execution in them to distinguish between the candidates. The generation of the world is done by another encoding as an SMT problem, but we will not go into details of it in this presentation. This is how the interactive synthesis works. What are its properties? When evaluating the interactive synthesis algorithm, we are interested in the answers to the following 3 questions. How much interaction with the user is needed, and how long is the waiting time for the user, which directly affects the usability of the system? What is the relative importance of the user's demonstration and the interaction with the system, and how the algorithm compares to competing methods? We created a list of 10 representative robotic specifications of size up to 5. It took on average 9.6 seconds and 2.4 interactions to derive the specifications, and we managed to do so correctly in 8 out of 10 cases. The evaluation shows that leaving out either biasing towards the natural language description or the interactions with the users results in a much worse performance. Finally, we compared the algorithm to enumerative synthesis using the same language bias. We run the enumeration for 20 seconds and count as a success whenever the correct specification is found within that time. That is, we are not considering at all how one would narrow from among all the found specifications consistent with the demonstration. Even with such a generous definition of success, our algorithm outperforms the enumeration in the number of successfully recovered specifications. It is worth mentioning, though, that whenever the enumeration finds the correct specification, it does so extremely quickly. The interactive synthesis algorithm is only a part of LTL talk. An equally important part and equally interesting part is the grammar expansion process. We use a domain-specific language that matches one-to-one to LTL in order to perform the grammar expansion. We are still using our example from the beginning. The user commands the robot to get one circle item from 7.4, which was determined by interactive synthesis to match the DSL expression eventually pick one X circle item from 7.4. The grammar expansion is based on the matching of partially parsable elements between the natural language command and the specification. For instance, the word 1 in the description matches the number 1 in the specification and corresponds to the grammar category number. Word circle is present both in the description and the specification, and it matches the grammar categories property and shape. Finally, numbers 7 and 4 are matched and they correspond to the category number. But the pair of numbers corresponds to the category location. Here we see that the design of the grammar is important for determining matches. Based on these matches, a number of new production rules is created. In our example, the grammar now contains expression get number shape item from number, as well as get number property item from location. The derivation of rules for augmenting the grammar is based on the work by Wang and others from 2017. The interplay of grammar expansion and the interactive synthesis is important. The interactive synthesis provides small building blocks which can then be combined and reused by the expansion mechanism. Let's consider an example instructing robot to visit the 4 corners with a fixed order of the visits. The LTL formula expressing that is a big nesting of F operators. However, we can define what it means to first go to 14.1 and then to 14.10. With that definition at hand, we can define the whole command in an easier and more natural way. Thanks a lot for your attention, and I'll be happy to answer your questions.